Okay, it's 3 o'clock on my computer clock, so I think we ought to probably continue. Yeah, and we're going to do that by getting started here with our next lesson on the basic concepts of thermochronology. And I think I pretty well appreciate the fact that things are jumping around a little bit and might seem a bit odd right now with the topics that we're being introduced to, but I can assure you that this will become more clear throughout the next few weeks. So don't panic if things seem a little strange and new in terms of the geological content here. The final part of the course will involve writing a short little report about something you've done in the last 2 weeks of the exercises in the course. And so that will be related to thermochronology. And in the past, I've kind of held off on introducing thermochronology until those last 2 weeks. And I think it's just not quite enough time for people to digest things. So we're going to introduce the basic concepts today because it relates to the diffusion equation and it relates to the exercise for this week. And we'll fill in the details along the way in the few weeks that come after this. So yeah, two goals here. One is to basically introduce what is thermochronology and what's the kind of idea behind it. And then we're going to talk about something called a closure temperature and the concept of a closure temperature and how we can estimate what those closure temperatures are. So this, I assume for most of you, this is going to be kind of new because it's not heavily used so much in Finland, although there are some thermochronological studies that have been done here and some that are even relatively recent. The reason that we're looking at this in terms of a general idea why it's useful, why do people use thermochronology at all, is essentially to study long-term processes related to tectonics and erosion. So typically it's applied in mountainous areas. However, there are good examples of these kind of studies that have been done in shield settings as well in Canada, in Russia, Sweden, Finland. So it's not exclusive to mountainous regions. But this kind of technique is used to study things like how tectonic processes and the rates of tectonic processes affect the Earth over millions of years. And so this is something that can be a little bit difficult to study with other methods. Same thing true for erosion. We can go and look at very short-term erosional processes by, for instance, just looking at how much sediment is moving through a river at some location. We can also go and look at things like deltas where there's been lots of sedimentary deposition, but it can be difficult to study things like the sort of uplands part of a landscape. So the mountainous regions where maybe that sediment is being transported from and deposited can be difficult to study over long timescales, and that's where thermochronology can be quite useful. I mean, as you would imagine, for things like deltas that are formed on sort of continents or margins of continents, one of the significant challenges there is that there's lots of places along the way where sediment from some mountainous region could be stored temporarily or much more long-term in a floodplain or something like that. So it's difficult then to link things necessarily from a delta to what's happening in the mountains where the erosion processes are kind of getting started. So that's the kind of overall view. We'll talk a little bit more about like some reasons why we're dealing with thermochronology in later weeks of the course. But our starting point here is to kind of make an important distinction between geochronology, which you might be more familiar with. This is the science of dating geological materials. And in this method, oftentimes we're using some kind of radioactive decay, so some parent isotope decaying to some daughter isotope or product. And in this way, this is actually true for thermochronometers as well. That's common in both geochronology and thermochronology if you're using a sort of radioactive source material as your way of measuring time. The distinction basically is in the interpretation of the ages. So for geochronological ages, we typically look at those as a crystallization age. So good example would be something like uranium decaying to lead. And that's a typical geochronometer, might be used, for instance, in zircons. So uranium lead decay, lead is a fairly immobile daughter product. So when the decay of uranium occurs and produces lead, the lead tends to stay more or less put where it is in the crystal. And as a result, then all you do is you measure the accumulation of lead, you look at the amount of parent isotope that is left over, and you can backwards calculate how long it took to produce that much lead from the decay of the parent isotopes. And that's basically typically how we would do a dating of crystallization, for example. It tells us basically when did that zircon crystal form. It's a little bit different with thermochronology because what we're dating in this case is often something that's interpreted as the time since the material cooled below some given temperature. So it's possible that a geochronological age and a thermochronological age could be the same. And this would occur, for instance, in some kind of ash fall or something from a volcano, where the crystals are formed at the time when they're erupted, for example, and the cooling occurs very quickly. And that very quick cooling means that the difference between the geochronological and thermochronological ages might be very similar. But the key thing is with thermochronology, we're basically dating the time since a given temperature in the Earth. And so these are often sometimes also referred to as like a cooling age. Let's talk about the concept here with a few additional terms. So when we talk about a thermochronometer, we're talking about an isotopic system that includes a radioactive parent, a daughter product or crystallographic feature. It doesn't have to be a daughter isotope, but it could be some kind of other daughter product. In some cases, it's something like a damage zone in a crystal that forms as a result of radioactive decay, and then the mineral in which this process is occurring. So that's our thermochronometer. So parent, daughter, and then the mineral in which it's occurring. So you can see, for example, here, some spontaneous nuclear reaction, and that would be happening inside a crystal. Now, there's a couple other terms here that aren't really super important for us. Thermochronometry and thermochronology. These are more just, if you come across the terms, it might be nice to know what the difference is between the two. Thermochronometry is usually referring to applying a thermochronometer to understand the thermal history of rocks. So we can, again, relate these different thermochronometers to different temperatures in the history of some rock. So its age might refer to a certain temperature, and whereas thermochronology would be the thermal history itself. These are not really so important to remember and distinguish between at the moment. But as I mentioned, both the reason that we can study tectonics, the reason why we can study erosional processes over long periods of time is that erosion tends to basically bring material from depth up toward the Earth's surface. So when we're eroding away rock at the surface, we're bringing rocks that are buried deeper up toward the surface. And the same thing can happen with tectonic activity too. For instance, in places where you have extensional faulting along the fault surface itself, you're basically exposing and exhuming rock from beneath the Earth's surface up toward the surface. And that's where one of the applications of thermochronology lies. We'll get into this more, I think, already next week in terms of thinking about what we want to do once we have an age or a closure temperature. But today we're just going to kind of stick to the basics. The essential kind of concept here is that we have basically two ways in which our crystal can behave. One is as a closed system. So the parent isotope here shown in gray, decaying to produce some daughter isotope here in white. And in the closed system, inside one crystal, the decay occurs and that daughter product is trapped within the crystal, doesn't go anywhere. This would actually be very much like how we think the behavior of a geochronometer would be. It's a closed system. Lead that's produced from the decay of uranium stays put inside the crystal. The open system behavior is the other part of thermochronology and what makes it kind of unique and challenging. And that is that in certain conditions, the parent isotope produces a daughter product, but the daughter product is not trapped within the crystal. So as we know with radioactive decay, we're continually producing these daughter products, but the question in thermochronology is, do you trap them in the crystal or are they lost? And this is essentially controlled by temperature. So at low temperatures near the Earth's surface, for pretty much every thermochronometer, when you have decay of the parent isotope to a daughter product, the daughter product is trapped within the crystal and it stays and accumulates there. At higher temperatures, and we'll talk about what high means in a few slides, that same daughter product is produced, but it may diffuse out of the crystal or otherwise be lost, so it doesn't accumulate, which means that if you were to go and date something, you wouldn't have any daughter isotope there to date at all. So this is the basic idea, the two different kind of closed system or open system behavior, which depends on whether you're at low or high temperature. Now, it's slightly more complicated than that because this temperature is not like a switch. It's not like all of a sudden you hit 200 degrees and you transition from open to closed. But instead, there's a zone over which you gradually decrease the likelihood that any daughter product would be diffusing out of the crystal. So if we're saying, for instance, this is a plot showing temperature going sort of increasing down like it does in the Earth. And here's the daughter concentration of the isotopes. You can see it's very low here at high temperatures. And then as we cross through this gray region, it's gradually increasing until we get up near the surface where you can see it's very high. It's basically all being trapped up here in the closed system part. So this would be the kind of top. Everything below the gray box would be the open system area. And then in between, we have this partial retention zone or partial annealing zone, depending on what we're looking at as a daughter product. But this is the area where we're trapping some of the daughter isotope that's produced. And we'll, again, talk a little bit about why that occurs. But that's the basic idea, is that it's not just like a kind of instantaneous switch. Now, the idea that we're going to talk about in the exercise today, and for I think most of the rest of the slides that we're going to go through here, is about this concept of something called a closure temperature. And the definition that's given here is up at the top of the slide. It's the temperature of a thermochronological system at the time corresponding to its apparent age. Again, this is one of these lovely sentences where you're probably like, what does that mean? But in essence, when we measure something with the thermochronology method, we get an age. Age might be 5 million years. The closure temperature here would be the temperature the rock was at 5 million years ago. So at the time, according to its age, its temperature at that point. And that's something we can estimate based on a method outlined from the 70s by Dodson. This is something that's still used today. Very simple conceptual model, but built on the ideas of diffusion inside crystals. And that's how this overall works. Allows us basically to come up with something that we can relate a measured age to a temperature, which is an important step we need to make. The thing is, when we look at these closure temperatures, it's not quite as simple as we might hope, because the closure temperature is affected by a number of different things. So not only does it vary from mineral to mineral, that probably makes some sense, but it also will vary depending on the size of the crystals and the chemical composition of the mineral and the rate at which the mineral is cooling, and several other factors, all of which will affect this closure temperature. So when you start trying to interpret, what does this age, what temperature does this age correspond to, there's a number of factors that you need to take into consideration. Just to give you some ideas, here's an example of how the cooling rate would affect closure temperature. So you can see cooling rate here. So this is basically how many degrees C per million years is the rock cooling down. So from 0.1 degrees C per million years up to 100 degrees C per million years. For geological cooling, other than, for instance, like a volcanic eruption, this is pretty fast, 100 degrees C per million years. That's very rapid cooling. If you consider that 100 degrees C here is probably something like 6 or more kilometers below the Earth's surface, you're traveling that distance in a million years. For a geological process, that's pretty quick. But what we can see here are some examples, and you don't have to look at all the different letters that are shown here, but this is the system for helium that's produced and trapped within an apatite crystal. And you can see that at low cooling rates, it's around 40 degrees for the effective closure temperature. At high cooling rates, it's around 80 degrees. So it's twice as high, depending on just the cooling rate for this one system. If we look at a higher temperature system here, this is for argon produced and trapped within hornblende. We can see that it's about 470 degrees at 0.1 degrees C per million years cooling rate. So very slow cooling would be there. And at a much higher cooling rate, it's nearly 600 degrees, or pretty much right on 600 degrees. So you've got 130 degree difference in the effective closure temperature as a function of the cooling rate. That's big. I mean, that's, if we're talking, depths in the Earth, that's kilometers difference in terms of what you're interpreting of, your picture of how this rock cooled down and came up to the Earth's surface. Now, regardless of whether we're looking at a thermochronometer or a regular geochronometer, there's an age equation here. You've probably seen this before, that allows us to calculate what the age would be of some rock sample or some mineral based on the amount of daughter product versus the number or concentration of the parent isotope, and then some production function here. So this is the radioactive decay constant of whatever the parent isotope is in this case. But with this information, so if we know something like the half-life and we know the concentrations of parent and daughter product, we would be able to generate then an age for how long it took to produce that much daughter product. That's the sort of standard view of how things work in a closed system. As we've mentioned, though, we don't always have a closed system with thermochronology. But I guess this age equation, I hope this is something you've seen before, and would certainly apply to uranium lead dating, for example. I mean, there's many others. Coming to our topic of diffusion, the reason why we don't have a closed system has to do with diffusion. So when we have these radioactive decay events, let's say uranium or thorium are decaying, most of the time, most of the decays are alpha decay, which produce an alpha particle or helium nucleus as a result of the alpha decay. So the decay occurs and you kick off a helium nucleus. So this is kind of what's shown schematically here. We've got some kind of normal atoms in blue. We've got some parent isotopes that have substituted into the crystal lattice in different places. And then we've got these green guys here that are the daughter isotope that have been produced from radioactive decay of the parent isotope and production of some daughter isotope here. Helium is an inert element. So when it's produced inside the crystal, it doesn't go bonding itself into the crystal lattice, but rather remains trapped between things that are in the crystal lattice. So it's kind of like a foreign isotope in a sense. And it's mobile because it's not locked into the crystal lattice. So it will diffuse and it will try and just move around randomly to find its way out of a crystal. And thus, it's perfectly suitable to model rather, this process of the diffusion that would occur for a daughter isotope like helium inside of a crystal as a diffusion process. And so here we have our diffusion equation. This might look somewhat familiar. Here we've got ND now for our daughter isotope concentration. So the change in daughter isotope concentration over time. Here's our diffusivity. So it was a D before, it's in a D here as well. And then we have our second derivative of the daughter isotope concentration over the second derivative in space, plus some production term. So we didn't have this before, but as we know, the decay is going to continue to occur. As long as there's a parent isotope, there will be radioactive decay and it'll be producing daughter product as a result. So we need to include this source term when we look at the concentration, because it's not simply redistributing the existing helium, but also accumulating more potentially. One other difference here is that our temperature, you can see our dT here, d and then parentheses T. This is our diffusivity, but it's temperature dependent here. So this is something we need to consider as well. It's not a constant that the rate of diffusion is the same irrespective of temperature, but rather temperature will affect the rate of diffusion of these daughter isotopes inside the crystal. Typically what we do when we model this is that the diffusivity, here d of T, would be modeled as being equal to some constant d naught. So this is a diffusivity at infinite temperature, or another diffusion constant, times e to the minus EA over RT. So this is an activation energy that's needed to start the diffusion process. R is the gas constant, and T, TK in this case, is the temperature in kelvins. And so this isn't sort of inversely proportional to the temperature, meaning that the diffusion rate in this case actually would be going faster and faster as temperature goes higher and higher. So it's actually, it is proportional in this case to the temperature. So our other thing that we don't have on here yet is this A, which is just the diffusion domain. So typically this is taken to be the size of the crystal. So 100 microns or whatever size crystal you have. If we just ignore those for the moment, we can drop the A's out of both of these terms if we wanted to. And we're left then with basically just seeing that we have activation energy divided by R over temperature. And that's raised to the minus EA over RT, meaning that as temperature goes up, the diffusivity will increase and it will become easier for material to diffuse more quickly inside the crystal. Another way to look at this is if we show, for instance, here, kind of cooling history. So you can see temperature going up here, time going off to the right. This is some curve where you can see the higher temperatures and rocks cooling toward the surface. For instance, as a result of exhumation, that could be one way to think about it. If we look here at the daughter to parent isotope ratio at these high temperatures up here, there's essentially no daughter product being trapped in the crystal. At some point, as you cool down a bit, you start to trap some of that daughter product. So now you're in the partial retention zone here, and you're trapping some daughter product. And as continued cooling occurs up to some point here, now you have a constant ratio of the daughter and parent isotope because the system is now a closed system and you're trapping everything that's produced. So there's a few different names that are used here. The closure temperature is the thing mostly that is going to concern us, because that closure temperature is essentially just an extrapolation of this daughter-parent isotope ratio curve. As if it was a straight line, it would continue down to this point here, which is basically midway or close to midway between the open system behavior and the blocking temperature where it's a totally closed system. So we're kind of somewhere not right in the middle, but close to the middle of the between the open and closed system behaviors. Okay. Any questions at this point? I hope I'm not kind of racing through this too quickly, but yeah, maybe let me know if there's any questions in the chat. If you're totally lost, that's also a perfectly valid thing to share at this point, just so I have some idea how things are going. I never really did much geochemistry as a student, so I'm not great about knowing how much you guys, like how much I can assume you know in terms of geochemistry. I'm definitely not an expert in that at all, but I assume you've had at least a little geochemistry, so some of these kind of ideas might look somewhat familiar. But if I don't see any kind of like, I have no idea what's going on stuff in chat, then I'll assume it's safe to continue, and we'll get through the rest of these lecture slides and then talk about a couple Python things and a little bit about the exercise for this week. So we mentioned this idea that in this paper in the 70s, Dodson introduced a way to define the closure temperature and how to calculate it. And the calculation was done essentially using a diffusion model with the simplification that we assume once the rock goes into the partial retention zone or the partial annealing zone, the temperature will vary as the inverse of time. So essentially, it's just kind of constant cooling through that partial retention zone. And if we assume that, then it's possible for us to calculate this effective closure temperature. We assume diffusivity here is going to follow this relationship where there's a connection between temperature and time. So there's a term here called lowercase Greek letter tau. It's the time taken for the diffusivity to decrease by a factor of 1 over E. If you've dealt with anything else related to heat conduction equations or diffusion equations in general, this is a common thing that's known as a characteristic time for the diffusion process. And it's basically how long does it take for the diffusivity to decrease by 1 over E. So that's a time scale associated with that. You could do a little bit of math, and the Dodson paper goes through this in more detail, but we don't need to worry about that too much. You come up with an equation here for tau that has the gas constant R times temperature squared divided by the activation energy over a cooling rate. And this is a negative term here because the cooling rate is negative by convention. So R would be positive, T would be positive because this is temperature in kelvins, so it has to be 0 or positive. Activation energy would be positive. Otherwise, we're defying the kind of fundamental physics of the universe. And then the cooling rate would be negative in order to get the negatives to cancel out and give you a time for tau that is a positive number. So there's that piece that depends on cooling rate and temperature. Then there's this closure temperature calculation itself. So this is calculating what the closure temperature would be. Activation energy has come back, as has the gas constant. Now we've got the natural log of A, which we haven't seen yet. It's a geometry factor. Tau, which is calculated up here above. D naught is the diffusivity at infinite temperature. And then A is this sort of spatial scale of diffusion, which is often, again, taken to be the size of the crystal you're dealing with. So the challenge we have here is that we can solve for this closure temperature by making the substitution that T equals Tc in the equation for tau. So if we, instead of putting in just T here, we put in our closure temperature, we can calculate tau. And then if we go here, we can calculate our closure temperature using tau. We have two equations that depend on terms in each equation. And so thus we need to iterate in order to find a solution for this. I'll talk about what iteration is, and you'll get to do this in the exercise for this week. But essentially, we can kind of make a guess at one of these things, like a guess at the closure temperature, use that guess to figure out what the tau would be, and then calculate a new closure temperature with that new version of tau, and just keep repeating that until the closure temperature number is not changing. So this is a kind of pseudocode for how to deal with Dodson's equations. So we have some constants we have to define, like the gas constant. We could take some initial guess for what the closure temperature would be. It should be some kind of high number. You could take like 1,000 kelvins just as a first guess. It should be in kelvins, so that's why you want to take a number that's big. And then you loop over some range and iterate on the values of tau and the closure temperature. And so you calculate a new tau with the current Tc, then you calculate a new Tc with the new value of tau. And you just kind of keep going through in a loop and doing that calculation. And you can then check to see at some point whether the value of Tc is not changing, which means you've converged on a solution. And if that's the case, you can then say, okay, we're done here. And that Tc value would be your final estimated closure temperature. So that's that part. If you do that using Dodson's method, you can do things like this plot, which is actually something we'll also do in the exercise for this week, and that is to calculate the closure temperature as a function of cooling rate. We saw something like this before, but this is the estimated closure temperature for apatite for cooling rates from 1 to 100 degrees C per million years. We'll calculate this over a little bit bigger range in the exercise. But what you can see, for instance, is the closure temperature goes up significantly as the cooling rate increases. And just to give you a sense, we haven't talked at all about the systematics of how these different systems are behaving. We might come back to that in a later lesson. But this is just to give you an overview of different thermochronometer systems. This is not even necessarily totally up to date. There are new systems that are kind of being worked on all the time. But there's essentially 3 classes. One of them is thermochronometers based on argon, being the daughter isotope, those based on helium, and those based on fission tracks. And so they're a little bit different with fission tracks between the others. The others, you're producing a noble gas daughter product that's just trapped within the crystal. But you can see here the sort of ranges of temperatures to which the different systems are sensitive. I'll warn you right now, the muscovite one is based on an older model. So that probably is too low for what we think for argon dating in muscovite. But give you some idea, it's about 350 degrees, probably realistically more like 400 or 450 even. For the uranium, thorium, helium, that's what's the middle range there. For zircon and apatite, those are 2 of the most common. Apatite's around 75 or 70 degrees Celsius, and zircon is closer to 200. And again, we'll see that in the exercise for this week. We'll calculate those closure temperatures and see what we get. And then finally, for the fission track systems, they're based on a little bit different systematics, but the same basic idea. So fission tracks are things that are formed from fission of uranium. So this is basically splitting the nucleus in half. And when that occurs, it sort of propels itself apart into 2 pieces and tears a damaged track through the crystal lattice. And you can then enlarge and date things based on the concentration of those damaged trails. And so if you do that in apatite, it's typically sensitive to temperatures around 110 degrees, a bit higher for zircon and titanite as well. So I think that takes us here. I'm not going to make you answer these questions about the basic idea for thermochronology or what an effective closure temperature is, but I would ask, do you have any questions at this point? So just to see if anybody's paying attention, if you were to give a number score between 1 and 10 in terms of how much you think you've understood about thermochronology, with 10 being I got all of it, I'm just right on top of it, and 1 being I have no idea, what number would you give for this quick introduction to thermochronology? So some number between 1 and 10, you can just type it into the chat. Just see if anybody's here. Okay. Okay. Got at least one person who's somewhat familiar. That's excellent to hear. So it looks like we got 5, 7s, somewhere in there. Okay, not too bad. I'm not seeing too many 1s, which is good. And I'm also not seeing anybody who says 10, which means that I had just sort of talked about something you already knew. That's also good. So thank you for the quick feedback. Good to see that people are here and listening. And yeah, let's maybe take a pause here. And I will exit out of these slides. And I can say a few things about the exercise for today. So on the course page, if you go here to lesson 3, you'll see we have the diffusion lecture slides. We have the basics of thermochronology lecture slides. Those are already up as PDFs. If you go to the exercise page, you'll see the red warning box here that says it's not quite ready yet. I want to look it over carefully before I post it, and it's close to ready, but won't be ready until this evening sometime. So I'll send a message in Slack as soon as the exercise is available. But in terms of what we have to deal with in the exercise for For this week, we're going to explore the diffusion equation, as you would certainly imagine. The first part will be just looking at some simple examples of diffusion of concentrations of, could be whatever, could be heat, mass, whatever, doesn't really matter. To just look at things like understanding what the diffusivity does. When you change the diffusivity, how does it change your diffusion profiles and things like that? And also looking a little bit at temperature dependent diffusion. So you get a sense intuitively of like what happens when temperature increases to the diffusivity and how does that change the rate of diffusion of material. So that's the very first part. After that, we dive into Dodson's equations a bit. We'll be adding some things to our intro QG functions, Python script file, which will be good because we'll come back to using those in later exercises. And the basic idea with this will be first you have to code up Dodson's equations. So we saw those. If I go, for instance, here to our lesson overview and the basics of thermochronology slides that we were just looking at, we saw, for instance, in here, the two main equations we're going to deal with. So one is this tau, and the other is the closure temperature calculation itself. So we will go through the process of creating a Python function with these equations in it. And then once you've created your function, you'll be asked to do things like look at a range of different cooling rates and how does that affect the closure temperature? Look at different grain sizes, so the different crystal sizes you could consider. How does the crystal size affect the closure temperature? And then finally, how does the thermochronometer system affect the temperature? So we'll look at a couple different thermochronometers using the activation energy and grain size and things like that that apply to those, the infinite diffusivity term that applies to different thermochronometers like helium and apatite or helium and zircon, etc. The thing for this is there's two new-ish things you might want to do. One is to consider an example of how to use a while loop. So we haven't done that in Fortran before. Maybe you've done it in other languages, but I thought maybe I could demonstrate for you, since we can't look at the exercise in detail at the moment, I could demonstrate for you how a while loop works in Python and why that might be a useful thing to use. And the other thing is that we are going to be doing some plots that show things like the closure temperature as a function of the cooling rate. I think we had one of those here, right? So we got cooling rate, closure temperature. You might notice that this is a logarithmic axis along the x-axis here. So 0.1 is equally far away from 1 as it is, and equal distance to go to 10, equal distance to go to 100. So this is basically log base 10 spacing between the points. So it's not a linear axis. And oftentimes these cooling rate plots are shown because you have cooling rates that range from, even lower than 0.01 or 0.1 to 100 on the same plot. It's often the case that you would then make this axis logarithmic scaling so that you can fit a broader range into a smaller space. So we're going to do that as well. And there's one NumPy function you might like to use that's mentioned in the exercise, but I thought I would demonstrate for you about how to, for instance, if you have a log axis, get equal spacing between the points where you're doing some calculation on that log axis. Because if you did this in another way with the linear spacing, like using the linspace function, you'll end up with very few points for the low values and many points concentrated up near the higher values in your plot, which might kind of make things look ugly. So let's take a look at a while loop here first. So it's a very simple demonstration. Let's just make a list here of names. And we'll put in here my name. And we'll put in Levy's name, even though he's not here. And we can put in Uncle Ismo from exercise number 1. And we can put in, I don't know, let's put in Woofy the dog. So a while loop is often used in a case where you want to do something until a certain condition is met. With a for loop, you say, okay, I want to do something a certain number of times. Like, if, for I in range 10 means you're going to iterate through your for loop 10 times. Now, we could take a while loop. It looks very much like a for loop. Instead of saying for, you just say while. And we could say while name is not equal to, and let's say Uncle Ismo. Then we could just say, let's do one more thing here. Name index equals 0. And then we'll just print out name at name index. And then name index equals name index plus 1. Okay, so we have made this list of names. We have this name index variable. It's just a counter, so it has a 0 in it to begin with. And we have this while condition. And then we have a print statement here that's going to print out the name at position 0 first, so it should print Dave. And then it's going to increase the name index by 1. So the next time through the loop, it should print Levi, and then Uncle Ismo, etc. Except our while condition is going to be also checking along here that whether our name is equal to Uncle Ismo. So in order for this to work, maybe we ought to do it like this, that we say names at name index does not equal Uncle Ismo. So that's going to be Dave first. Dave does not equal Uncle Ismo. So this while loop will continue. And then the next time through, it should be equal to Levi. It should print that name out. And then the third time through, it should hit Uncle Ismo, and it should then stop at that point. So if I run the cell, I see Dave, I see Levi, and I don't see this because now this condition is no longer true. Names at name index, and by this point, name index is equal to 2, which means the name is Uncle Ismo, and Uncle Ismo does not equal Uncle Ismo is false. And so then the execution in that loop stops. Let's look at another example. And this is a kind of fun one that I just happened to have found online that you might also, I don't know if anyone would enjoy it, but let's imagine that we want to use a little trick for calculating the square root of a number. And I found a nice example of this where we could say our number, and let's start with something simple like 121. So square root should be 11. And then we have our guess. And our guess in this case, we can say is, let's take something like half. We know it's going to be less than that, but let's just say our guess for what the square root is 60. We could then have, for instance, one example would be a for loop. We're going to use a little iterative solution here where we say our guess is equal to 0.5 times. You don't need to worry about the equation here. Our guess from before plus the number divided by the guess from before. So we have a number, we want to calculate the square root of it. We have our guess for the first try of what the square root would be. And then we have a for loop, and we're going to go through here and we're going to recalculate what that guess is using this equation where we take the original guess plus the number that we have divided by the guess, and then we multiply that by 0.5. In the end, after those iterations, actually, let's print it out here. So let's print guess along the way. And so when we run this, what we see is the first number we get is 31, then 17, then 12, then 11 point something, 11.000, 11 point lots of zeros, and then it's pretty much 11.0. So it found pretty quickly, within about 6 iterations, it found the square root to within 16 digits of precision. So that's a pretty quick way to find a square root. Now, I don't know if this gets really nasty if we start putting in really big numbers. I guess we don't want to put letters in there. So here with 10 iterations, we probably have not found our solution. If we give it 20, okay, so it finds it within somewhere between 10 to 20 iterations. If we start putting in bigger numbers for the number that we're trying to get the square root of, let's go back to the world where we can handle things with more reasonable numbers. And in this case, I guess this ought to be 72. In this case, we could run our same for loop, but we end up in more than half the time just wasting calculation by doing the same calculation over and over again. So let's take the same thing here and reconsider this example as a while loop, or using a while loop. So instead of for I in range this, what we would do is we would say, make another variable here called guess difference. Well, let's just call it guess diff. And let's just start, it's 1.0. So we have our guess here. We're going to take that as when we come in here. Before we recalculate, we can say that our guess original is equal to guess. So we come into the for loop, our guess is 72. We're going to store that number here as guess original. Then we're going to recalculate what guess is. And then at the end of this, we can say our guess diff is equal to the absolute value of, let's say, guess original minus guess. So what this is going to do is just take our original number we had that we thought was the square root, calculate a new best estimate of it, and then take the difference between the two numbers. It's going to give us some number back. If it's initially, it's probably going to be pretty big. Now, our for loop, we could change to being a while loop by just doing the following. And we say that while our guess diff is, let's say, greater than 0.01. So as long as the difference between our current estimate of the square root and the previous one is bigger than 0.01, keep guessing. As soon as you reach the point that that's no longer true, you found your square root, and at that point, you can then stop doing your calculation. This is a very typical way in which you would use a while loop. So we could then print out our the square root of number is guess. So if I run that, I see here that the square root of 144 is 12.000000, and then some stuff here. Now, the reason we've got this and not exactly 12 is because our criterion for what we considered to be a sort of small change in the number was pretty loose. We said that it only had to be to the hundredths that the number was changing. We could add a bunch of zeros here, and now we see the square root of 144 is 12. Now, just because I'd like to demonstrate it, we could also add in here a counter, where every time we come in here and iterate, we could just say counter equals counter plus 1. So this is just going to add 1 every time this while loop runs. And so we could then say the square root of this is this. So square root of 144 is 12 after some number of iterations. So if we run this, we say the square root of 144 is 12 after 8 iterations. If we make this criterion less restrictive, like we had it before, we see the square root of 144 is this after 6 iterations. And if we put it back up to what it was and then give ourselves a much nastier number, we see that the square root of this is 377 point whatever after 13 iterations. So the point here is that this kind of convergence of a calculation is something that's often done with a while loop. You can use a for loop to do this in the exercise for this week. But if you're looking for a challenge, you could also think about like whether you would want to try and do this with a while loop. It's kind of fun in a sense because you don't do any more calculations than you need to. And you can say, for instance, here that my estimate needs to change by no more than this in order for me to be happy with the estimate being a good calculation. And this kind of iterative thing is going to happen for the closure temperature because you're going to calculate tau, then you're going to calculate a new closure temperature, and then you're going to say, well, has my closure temperature changed? Yes or no. If it has changed by some certain amount, then you go and calculate tau and the closure temperature again, and you do this iterative process in order to find what the closure temperature should be. So that's an example there. Maybe I'll try to add a couple notes and put this up on the course page as well. The one other thing I wanted to show you quickly will require NumPy. And I'm going to go ahead and import matplotlib as well, just so I can show you a plot. So I'll just import those two quickly. Let's imagine we want to have the numbers between 0 and 100 in, let's say, 11 steps. So we could say, for instance, make an array of values called x. That's just np.linspace. Might remember this from the first week. 0.0 to 100.0 in 11 steps would give us 11 numbers from 0 to 100. Run that. And if I look at x, then I see, sure enough, there's my numbers as expected. If we were to do the same thing, but we want to have equal spacing in logarithmic space, we can do np.log space. And here, I think actually let's make this go from like 0.01 to 100 because it's log of 0 is going to be a bit of a problem. But if we said linspace was this, okay, there's our X array. It looks pretty similar to what it did before, but now we've got some extra stuff. 0.01 to 100 in 11 steps. If we wanted the same range in logarithmic spacing, here, what you do is you say 10 to what number would give me 0.01, and it would be 10 to the power of minus 2. 10 to the power 2 would give me 100. So here you're giving like the power at which you should raise the number 2. And then again, 11 for the number of values that you want to calculate between log or 10 to the minus 2 and 10 to the 2 power. So if I look at x2 now, I see I start with the same value, I end with the same value, but the points are much more closely spaced together for the small numbers and more distantly spaced apart for the big numbers. The reason that I had decided to load this in as a plot was to be able to do plt.plot of x, for example. If I do that just by itself, actually, let me make x, and I'll just put this O in quotation marks so it uses circles to plot the points. This is just the index along the x-axis, and then this is the value itself. So you can see at index 0 in our array, we have 0.01. At index 10, we have the value of 100. So this is just increasing at a constant rate. So let's say that this is AX equals plt.plot XO. We could then say AX.plot x2, and let's make this red dots, red circles. Add the log spaced points on there. List object has no. All right. So I guess I have to make a figure first. So I'll do that using plt.subplots. There's some tips about doing this in the exercise, so don't worry about that. So then we'll just do ax.plot and ax.plot with our two different things there. Now you see that this is the index still along this axis, along the x-axis here, but then the y value is the value in x2 or x1. And you can see the x2 values are all kind of very low, and then they kind of rapidly increase. And that's because if we were to take the y-axis and make the y-axis a logarithmic axis, these points would then be equally distributed. So let's just do that. And then I should let you go because I'm going to run out of time here. But if we did ax dot, I think it's set y scale. Sorry, I'm kind of running out of space here. Set the y scale to be log. Same plot as we had before, but now the y-axis is logarithmic. You can see here, log axis. And now you can see these points are equally spaced along the vertical axis, and these are the ones that are in log space. So when you have values where you're going to plot them along a log axis, it's often useful to use this log space function to keep the points equally spaced, because for instance here on this log axis, when we had linear increments between the points, so equal spacing between all the points on a linear axis, you could imagine that between the first point at the rate of 0.01 and this point here, you've lost actually quite a bit of range in terms of the rates that we might be interested in, that are just not going to be represented very well. And this would just be a straight line connecting these 2 points, when in reality, the shape might look a bit different. So I don't know whether that totally made sense to you, but you'll see in the exercise for this week that for the problems where you have to use a log x-axis, that I recommend you use the log space function to generate points that are equally spaced along that axis. But yes, I fully appreciate that this might be a little confusing, so I will try to remember to dump this notebook up on the course page so you can have a look at that. And I'll try to also maybe add a few comments so you can see that. Are there any questions at this point? So I've gone quite close to the end of our time. Sorry about that. But I'll get the exercise up on the course page sometime this evening. I've got a couple hours drive before I need to do that. So it will probably not happen until later this evening. But as soon as possible, I'll get the exercise posted. And then if you have questions about that, you can feel free to ask those there. And there were some comments in Slack about having some kind of online, either Zoom or Slack-based discussion on sometime toward the middle of the week. Maybe we can try and do that for the first time this week. So I'll also try to put something in Slack just to note when we might be able to have a sort of extra support session. So if you have questions after looking at the exercise, you could then either come to Slack or join Zoom at the designated time, and we could then go through at that point how to help with your questions. But yeah, if there's nothing else at this stage, I think that's it for today. As I just mentioned, I will be kind of driving for a couple hours this evening, so it may also delay getting the lesson video posted. I'll try to post that as soon as possible. But yeah, hopefully next week we'll be a little more caught up on things. Made major changes to the exercise for this week, and that's been just a far slower process than I remembered. I probably should know better, but I just forgot how long it takes. So we'll see if we can get things back on track for next week. But in the meantime, if you have questions, just feel free to ask them in Slack. And otherwise, we'll catch you in Slack or Zoom midweek or on Friday at the exercise support session. So see you guys later this week.